Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to go over how to identify conjugate bases from their acids. So like the last video I did, I showed that how to go from your given base to the conjugate acid. So in this way we're going to go in the opposite direction, but the strategy is exactly the same. So I'm going to show first like how this happens in water, and so how the conjugate acid and base are related to each other. So I'll use A as an example. So here they're asking for the conjugate base. Well, you have to understand that the conjugate base comes from an acid. So here we're given acids or species we're supposed to treat as acids under this context, and then produce what the conjugate base would be. So if I react, for instance, HCO3, or I'm sorry, HClO3, let me write that again. HClO3. And if this reacts with water, right, um, because it's an acid, it's going to want to donate this hydrogen to water. So here we're thinking of this as a Bronsted-Lowry acid. It's going to donate a proton or a hydrogen to water. In this context, water is behaving like the base. The Bronsted-Lowry base accepts the proton. So in this case, it's water. So then we're going to form what's left after this is this ClO3. So the ClO3 with a minus now, plus the hydronium ion with a positive charge on it. And so you can see here the relationship between the acid and its conjugate base. So here, just to reiterate that the acid and the base are always going to be on the reactant side. These are not conjugates. The conjugates are always going to be on the product side. So this is our acid, right? The conjugate base comes from the acid. So when you donate the hydrogen to water, what's left? You got the ClO minus. So this is your conjugate base. And the key here is the difference between the acid and its conjugate base is the transfer of one hydrogen. You can transfer a hydrogen between them. So the difference between the acid and the conjugate base is one hydrogen. So in order to get your conjugate base, you're going to lose the hydrogen from the acid. In this case, water is acting as the base. Here, let me link these together. So the acid and the conjugate base are linked together. And here the base, water, that's going to accept a hydrogen. And so the difference between the water and this is one hydrogen. So this gains the one hydrogen. So this is going to be your conjugate acid. Well, why do we say acid? Because if we go in the opposite direction, the hydronium ion would lose or donate the hydrogen to something else, right? So it can behave like an acid in the opposite direction. So the difference or the relationship between your acid and your conjugate base, or your base and the conjugate acid, is going to be the difference of one hydrogen. So your acid will give the hydrogen away. What's left over is the conjugate base. Your base is going to accept the hydrogen, the result of which is your conjugate acid. So we saw about conjugate acids in my last video. So here we're doing conjugate bases. So the answer to A is going to be the loss of a hydrogen. So your conjugate base is going to be whatever acid you have minus one hydrogen. So here we lose a hydrogen, so we get what's left, ClO3 minus. So that would be the conjugate base of this acid. So if we go to B, here, this would, in the reaction of water, donate a hydrogen to water. So it's going to lose a hydrogen. So what's left is the conjugate base. So HSO3 minus. hydrogen sulfate ion, or sulfide ion, if you will, is going to be the product or the conjugate base of this acid. Here we have water. Last time we saw water, it was acting as a base. Here it's going to act as an acid. So it's going to donate a hydrogen. This is the autoionization of water again. So it can donate a hydrogen to another water molecule. And so in so doing, it would end up having an OH minus left over. So that is the conjugate base of this acid here. Again, here, this is our acid, so it can lose an electron, it can lose a proton or a hydrogen to water. So then what's left over is your C3O or your CO3 minus, your carbonate ion. Again, next we have H2C2O4, oxalic acid. And so here, it's going to lose one hydrogen. So what's left after losing one hydrogen to water or whatever it is? So there would be HC2O, oops, that should be an O4 minus. Next, we have HBrO4. This would be bromic acid, or perbromic acid. And so in this case, it would lose a hydrogen. And so what you're left with is BrO4 minus. Ammonia. So before we saw ammonia acting as a base, here we're going to see it acting as an acid. So again, it's going to donate one of its hydrogens to water or some other species if there's another base or stronger base around. So here, it would become NH2 minus. So it loses a hydrogen. So there's your conjugate base. And then finally, we have H2PO4 minus. So that's going to lose a hydrogen. So what's left is the conjugate base. So that's going to be HPO4 2 minus. And so that is the conjugate base of this acid. And so that, ladies and gentlemen, is how you determine the conjugate base of a given acid. The acid is going to give away one of its protons. Whatever's left is your conjugate base, because that can then go back and take a proton back and then reform the acid. So I hope this was helpful. If it was, then please, by all means, like the video, hit that like button, share the video with your friends. Also, make sure you subscribe to my channel, hit that notification bell. When you do, make sure you click all so you can be notified by all the videos I put out. And then finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. If you have a problem or a question you need help on, or if you have a topic that you want me to cover in a video, I would love to do that for you. Thanks for joining me and have a great day.